Hello everyone, I'm Chaoyu Guan from Tsinghua University, and I'm currently at my third year pursuing my master's degree. And it's a great honor to be invited by Hong Kong Machine Learning Group to share our research works with you. Today I will introduce you the AutoGL library, which is developed and maintained by our Media and Network Lab. The AutoGL library is designed to perform automated machine learning on graph. Our homepage, GitHub, and the documentation and the paper link is shown below. And I recommend you to take a look and give it a try if you are doing some projects or problems related with graph learning. So today, I'd like to share you the following topics. At the beginning, I will give an introduction to graph and graph neural networks and how they are applied to the real-world applications. And then I will share our AutoGL, a library for automated machine learning on graph with you, in which you can learn about how we decompose the problems, develop each part with suitable algorithms, and put them together. At the third part, I will walk you through some basic starting codes of AutoGL. I will demonstrate how to install and use our AutoGL library and show some examples on how to perform AutoML on graphs using our library. So at last, I will share some related resources for you to learn more about our library and other related works in our lab. Hope you can enjoy this talk. So in the first part, I will introduce the background of graph and graph neural networks and the drawbacks of the current solution in the graph learning. So as we know, the graph data is everywhere in our daily life. For example, all the people in the world can be seen as a big graph. If we regard each person as a node and the relationship of them as ages, the social graph is then constructed in this way. Similarly, the compound in the biology, the financial relation, the Internet of Things, and the information transformation network, and the logic inference can also be seen as a various form of graph. Even the image and the language can be seen as a graph of special form, connecting the pixels and words together. Also, the graph form itself is very important. For example, in chemical and biological fields, the biology structure is very important to the functionality of the medicine. In NLP, the knowledge graph is widely used to embody common knowledge to the models. In the recommendation, the relation information is extracted from the social network to help make better recommendation for users. And in language modeling, the semantic and syntactic tree is also widely used to help boosting performances. There are more and more research and application fields that need explicitly considering the relational structures of the data. So in general, there are three main problems in the graph learning field, namely link prediction, graph classification, and node classification. The link prediction aims at predicting the potential links given the observed graphs. For example, given the observed relation among users online, we can predict the relationships among unlinked users to make better recommendation for the new friends. A graph classification aims at predicting the label given the whole graph. For example, in medical area, instead of conducting time and resource exhausted chemical experiments on the new drugs, we can instead predict the attributes and the properties directly using the structures of the drugs. And the node classification aims at predicting the label of the nodes given part of the observed node labels. For example, we can predict the ages, career, or other attributes given the social network, which can better help profiling the users online. In addition, there are many other tasks under graph learning area, leading to various graph learning scenarios. So the most famous solution to the various graph learning tasks is graph neural networks, especially the spatial graph neural networks. The basic spatial graph neural networks can be abstracted as a message passing frameworks shown below. At every layer of the graph neural network, the node will aggregate the features from its neighbors to form the new feature. The formulation is shown below. For a node I in the layer L-1, all the features of the neighbors will first go through a function g together with the feature of node I and the age connected with them. Then the output of g is pulled for all the neighbors. Then the pulled features will go through function f to obtain the new features of the next layer. So for example, If we have a graph that have 4 nodes represented on the left of the slides, then for the node 1, it will aggregate the features of node 1 and node 2. For node 2, it will aggregate all of the node's features. And for the node 3 and node 4, they will aggregate features of 2, 3, and 4. However, how to design a good graph neural network is very hard currently. Even for the same graph learning tasks, best model and best hyperparameters may vary and need heavy human designing and tuning. The most important steps are how to choose the function of G, pooling, and F. Currently, there are some golden designs like GCN, SAGE, GAT, etc. Their design of these functions are shown in the slides and are proven to perform better in some scenarios. However, the search space of the total possible architecture is very large. The table listed on the right of the slides shows some common used designs for the GNN model. This results in a combinatorial design space and lead to around tens of thousands of combinations for just one layer GNN, let alone GNNs with multiple layers, which is much more complex than one layer GNN. So actually, the graph model construction is only a part of the whole graph learning pipeline. When the data or a task is obtained, there are mainly 4 steps before deployment. First, data preprocessing is done to download, manage, and clean the target dataset. Then, feature engineering is performed to generate or compress the features for the node and graphs to keep the valuable information while discarding the useless one. Then, a graph neural network model is constructed to model the relationship between input graph data and the target labels. At last, the model is trained and evaluated to optimize the parameters and select the best one for the deployment. Note that all these steps need tuning of hyperparameters, which lead to harder optimization, more trials and errors, and heavier resource and time consumption. To solve the challenge in the last slide, we propose AutoGL, an automated machine learning framework on graphs. Instead of manually training and evaluation, instead of manually design all the modules of the data preprocessing, feature engineering, model construction, and model training and evaluation, we let the machine optimize and choose the best one for us. So the pipeline will become the bottom part. In our AutoGL, the data processing is handled by the AutoGL dataset, which will automatically download and preprocess dataset. Then auto-feature engineering is performed by using some importance measures to build meaningful graph features. Then the neural architecture search is conducted to automatically find the best neural architectures or same models for the target task. Then the architectures are trained and optimized in an iterative way to optimize both the learnable architectures, the learnable parameters, and other hyperparameters related to models and the training procedure. At last, an auto ensemble is performed to make use of all the best models found in the previous pipelines and construct a more powerful system. Compared to the manually designed pipeline that need expert knowledge, tedious trial and error, and has low tuning efficiency and limited by human design, an automated graph learning framework can free human out of the loop, enjoys high optimization efficiency, and can discover and extract patterns and combinations automatically to enlighten experts to design better graph learning system. So next, I will introduce you the detailed information on the automated machine learning on graph. So actually on the library side, there are many existing libraries for graphs and for AutoML. For example, the PyTorch geometric, deep graph library, etc. If you are aware of graph learning fields, and H2O, AutoKeras, or the newest neural network intelligence from Microsoft, if you are aware of tabular or AutoML fields. However, these AutoML libraries cannot be directly applied on the current graph learning libraries because the uniqueness of the graph data and model structures, and the complex and diverse graph tasks, and a very important problem that graphs in the real applications are very large and it's hard to sample in the IID form. Therefore, there exists a large gap to apply AutoML on graph area, and a library specifically for AutoML on graph is lacked. So because of this reason, we present our library AutoGL to bridge the gap. AutoGL is an AutoML framework and a toolkit for the machine learning on graphs. Our library is open source and is designed on purpose to be easy to use and flexible to be extended. Our library is now online available on the GitHub, and if you can you can find it at the URL shown below, or directly search for the AutoGL. So our AutoGL system is designed in a modular manner. We separated the AutoGL pipeline into seven modules. The first one is AutoGL dataset, which is used to manage the input graph data. Also, you can directly use famous datasets online to conduct AutoGL experiments by only specifying the name of it. Our AutoGL dataset will automatically download, manage, and preprocess the contents for you. And the second large module is a high-level AutoGL solver. It will take the AutoGL dataset as input and build the whole graph learning system for the specified dataset. The solver will make use of other smaller modules to build the automated pipeline and allocate the computation and the time resource wisely. Then, additional 5 functional modules are maintained to provide finer-grained AutoGL tools, namely auto feature engineering, neural architecture search, hyperparameter optimization, model training, and auto Ensemble, which is introduced earlier. And in the following, I will introduce in detail every part of our AutoGL, including the supported algorithms. So for the auto feature engineering, the auto feature engineering handles the engineers of features specifically on graphs. In our implementation, we separate the feature engineering into 2 parts, the node level and the graph level. The feature processed in the node level will change the features of the graph nodes, while the features processed in the graph level will directly generate features for the whole graph. For the node level feature engineer, we further separate it to generators and selectors. And the generators will generate new informative features based on the current features, while selectors will compress the current features to eliminate the noisy or useless information. For generators, our library now supports algorithms like GraphLet, Eigen-GNN, PageRank, OneHot, etc. The transform module in the PyTorch geometric is also directly supported to be PyG user-friendly. For the selectors, we support filter, GPDT, etc. For graph-level feature engineering, we support all the methods in the 2 most famous libraries, namely NetLST and NetworkX. And for the neural architecture search, the neural architecture search aims at finding the best graph neural architectures for the current tasks. In this module, we support both graph-agnostic and graph-aware algorithms. Systematically speaking, we first split neural architecture search into 2 submodules, named algorithm and search space. In this way, we can implement more kinds of neural architecture search frameworks by combining different algorithms and search space together. For algorithms, we further support random search, one-shot based search, and reinforcement learning based search algorithms. In more detail, the one-shot based search algorithms include the famous algorithms in computer vision, like efficient neural architecture search and differentiable architecture search. The reinforcement learning based algorithms contains banana reinforcement learning methods from the computer vision area and the graph-NAS methods proposed specifically for graph. While for search space, we mainly support 2 kinds of space for graph neural architectures. The first one is borrowed from the graph-NAS, where the macro and the micro search space is both included in the library. The single path search space is borrowed from the paper Single Path One-Shot Neural Architecture Search with Uniform Sampling, where the operations as a whole, like GNN, GCN, GAT, etc., is used to construct the graph neural networks. So after the model is constructed, the hyperparameter of the model and the training procedure need further optimized for better performance. In this module, we also support general purpose algorithms and graph-aware algorithms. For general purpose algorithms, we support most of the popular ones like random search, Bayesian optimization, grid search, anneal search, tree-structured parsing estimator, and KMES, etc. For graph-aware algorithms, we support AutoNE, which is also an earlier work in our lab to find the best hyperparameters through sampling and meta-learning. So the model training module is similar to the one in the PyTorch Lightning, with some support specifically designed for the automation of the pipelines. Currently, the 3 most popular tasks including node classification, link prediction, and graph classification are all supported. The model training part handles various hyperparameters within model and training procedure. For example, the learning rate, the learning epochs, optimizer type, loss function, and early stopping epochs during training, and the forward implementation, the choice of operation and of architectures, and the dropout rate, and the hidden size of the model. So at last, we will ensemble the models trained with well performance to form a more powerful and robust system. For each ensemble model, we also support two kinds of algorithms. Voting will account on the vote of each base graph learners to make the final decision by choosing the prediction that receives the most votes, while stacking decides on another meta learner to learn the mapping from the output of the base graph learner to the final targets. In stacking, we support general linear models and gradient boosting machines as the meta learner. So this slide shows some of the performance of our library compared with previously handcrafted and tuned results. From the table, you can see that the graph learners optimized by our library can always outperform the previous models on both node classification and graph classification tasks. On some graph classification dataset, we even can increase the performance of the baseline with more than 5%. We also test the HPO module in our library, which is responsible for the most performance gain. From the table, we can see that as the trail numbers increase, the performance becomes better. Under a modest hyperparameter setting, the performance can match up or even outperform the carefully tuned models with only 10 times of trails. And the 50 trails can further push the performance forward with up to 1%. So currently, AutoGL is at its 0.2 version, and we are busy moving forward to the 0.3 version recently. So in this new version, we will support deep graph library backend and provide systematic support on larger scale graphs through sampling and distributed training. And also support more kind of graph learning tasks and auto methods like heterogeneous graphs, spatial temporal graphs, and auto attend. We warmly welcome all kinds of feedbacks and suggestions. If you like, you can contact us through autogl@tsinghua.edu.cn. We will answer your questions and take actions at the first time. So at the third part, I will briefly guide you through how to install and use our AutoGL library. Note that all the scripts can be found in our documentation. You can read more in our documentation if you are unclear of the functionality of the code or are interested in more details about our library. So the first step is installation of our library. The AutoGL is based on the PyTorch geometric backend. So we need to first install PyTorch and PyTorch geometric library. This can be found on the website of the two libraries. Currently, there are two ways of installing our libraries, through pipe or through the source code or on the GitHub. For time reasons, here I only show you how to install through pipe. The command line is simple. You can directly install it by typing pipe install AutoGL. So I will give you an example quickly on the Colab. So this is a Colab NumPy notebook. So let's first check the environment, and you can see that it's an environment with CUDA version 11.2 supported. And by default, the Colab by default can provide the PyTorch library, and you can see the PyTorch version is it's a bit low. So you can check the PyTorch version through this command line, and then you can install the PyTorch geometric library on condition of the given the PyTorch version. So you can install the PyTorch geometric library through these command lines. And please be aware that our AutoGL at 0.2 version only supports torch geometric. in the 1.x versions. So we currently we don't support the touch geometric on the 2.x versions. So you need to specify the version here. And then you can install the AutoGL by directly pipe install AutoGL, and it can handle the dependencies automatically. So it's done. And you can then import AutoGL and say the version should be 0.2. Yes. And for the next part, I will give you an example on how to perform node classification on a common dataset named Cora. The Cora dataset is a dataset of papers and their citation relationships. The task of the dataset is to predict the type of the research fields of the papers, which can be seen as a node classification task. So for the node classification tasks, what you need to do is to if you want to perform a node classification on Cora dataset, you can first import the build dataset from name function from our library, and then you can directly call this function to get the Cora dataset, and then you can build a solver or build an auto node classifier using this command line by specifying the feature module and a field module to it, and then you will obtain a solver that can conduct the AutoML on Cora directly. Then you can fit on Cora dataset. Then you can see that the HPO module is on its way by searching for the best models. It will take some time. So we can see this later. I can go forward. So at the last part, I will introduce you some related resources with AutoGL and some other projects related with our AutoML in our lab. So if you are interested in the more detailed description and evaluation of our AutoGL, you can find our paper, AutoGL, a library for automated graph learning on iClear 2021 workshop on GTRL. If you are more interested in the detailed information of the algorithms, you can find our survey named Automated Machine Learning on Graphs, a survey on EGCAI 2021. Also, there is a competition team in our lab named Meta Learners that is actively on all kinds of challenges related with AutoML. So currently, our team has won many prizes listed below. And if you are interested, you can visit our GitHub at the github.com Meta Learners. So let's see. Okay, so the code has done the AutoML on the Cora, and then you can get the leaderboard through this command line, and you can see that the GAT model gains the best accuracy on the validation dataset, and then you can predict on the Cora on the test part of the Cora, and then you can get the accuracy output, and it will give you an 0.828 accuracy, and it's very relatively it's very high on the Cora dataset. So that's all for my today's sharing on AutoGL, and thanks again for the invitation from the Hong Kong Machine Learning Group, and thanks for your listening.